With our discussion of electron configurations, we know the things that we need to think of when we put together the configurations, and we are going to create a different way to represent the electron configurations. It's not practical to be drawing the orbital diagrams and all those boxes, which I have very properly color coded here. You see all the s orbitals have a color, p orbitals have a different color, and d orbitals have a different color. So that's not practical. So what do? We create a different way to express, to represent that information. And what we do is that we're going to write the symbol of the element that we're representing, and then we're going to have the sequence of the orbitals, like 1s, 2s, 3p, 3s, 3p, 3d, and so forth. And where the number, again, will represent the shell, or the value for n, the letter will be the subshell, or L, and we don't represent m sub L, we'll see why. And then as a superscript, we're going to have the number of electrons that are present in that type of orbital. That would be the number of electrons that correspond to that subshell for that atom that we're representing. In this case, we have 8 electrons. So the sum of the superscripts here should add up to 8, 2, 4, and 4, 8. That is correct. And we evidently don't need the other orbitals, because we said that when we do the configuration, we only have those orbitals that are occupied, that have electrons. We can do away with the others. And we have, we may be wondering why we do not represent some m sub L quantum number here. And that is because, once again, the m sub L values are degenerate, so there's no need to represent them separately. So yes, you're totally right. We have 3 2p orbitals, and here it says only 2p. That 2p represents the 3 of them. Okay, we don't really care here if they're x, y, or z. What we care about is that we have 4 electrons distributed in those 3 orbitals. And of course, when we have the diagram, the orbital diagram here, we can also just ignore the orbitals that are not occupied. So we simplify both of them, the electron configuration and the orbital diagram. So we've talked about 3 different things: the energy diagrams, the orbital diagrams, and the electron configuration, and we need to be able to name them properly and not get them mixed up. And here I have the the energy diagram for a multi-electron atom. We see that the orbitals within a shell are not all of them degenerate, but the orbitals within a subshell are degenerate. And we are going to see how that affects the sequence, how the electrons fill up the orbitals in an atom. I just have here the ground state electrons for elements lithium through carbon. You can do this as an exercise at home. We have the number of electrons, and again, the number of electrons must be equal to the sum of the superscripts here, because the superscripts represent electrons. One definition, 2 definitions here. Valence electrons and core electrons. You might have heard that from high school, and you probably know this already, but just to make certain, we define the valence electrons as those electrons which are in the outermost shell of the atom. So it would be the orbitals that have the highest n value for that atom. Like for nitrogen, these would be the 2 orbitals, 2s and 2p. Those would be the valence electrons. If electrons in an atom are not valence electrons, we call them core electrons. So the core electrons for nitrogen would be the 2 electrons that are in the 1s orbital, and the valence electrons will be the 2s electrons and the 2p electrons. And notice here how I referred to these electrons as the 2s electrons. That's a sort of a shortcut, because those are electrons that are in the 2s orbital, right? But since the electrons are there, we attribute that label to the electrons as well. Okay, so we've defined valence electrons, core electrons. Again, that picture that shows us the difference between the one electron atom and the multi-electronic atom or multi-electron atom, and how the sequence of the orbitals changes. The sequence is, there's a rearrangement of the orbitals. And once again, remember that this rearrangement is caused by repulsions amongst the electrons. If we have more than one electron, the electrons are going to repel one another, and they're going to change, they're going to modify the potential energy. So they're going to acquire different energies. But still, within a subshell, there still are, they will still be degenerate. And the approach that we can take to this is to explain, to describe the way that nature operates, instead of trying to predict what nature does. So when we go in and we run our experiments, we realize that this sequence that I've got here is what is actually observed, and we can observe that by doing the spectroscopic experiments. We see that this is the sequence, that we go 1s, 2s, 2p, 3s, 3p, and then the next one of lowest energy that's available is 4s, and then 3p. So instead of going from 3p to 3d, it goes from 3p to 4s, 3d. How do we know that? Because that's what we observe in nature. An easy way to remember this sequence is to just write all of the s orbitals down in one column, then all of the p orbitals, then d, and then f, and the sequence, the way in which the orbitals are filled, goes from top to bottom diagonally. Okay, so we filled out the 1s, then we go up 2s, go up 2p, 3s, 3p, 4s, and so forth. How do we know that? Because that's the sequence that nature has shown us. So there is a difference here from what we expected. The way we had it for the hydrogen atom, the sequence would be 3s, 3p, 3d. The 4s gets lower in energy than the 3d, and that's why it is filled first. You can do this exercise of taking this periodic table and try to label or name the different regions of the table. For instance, you could try to find out where the metalloids are, which color is represented by the metalloids, which elements are the halogens, where are the alkaline earth metals, and so forth. That would be a good exercise. And this table is color coded. There are other things that we could add to it. For instance, which elements are gases at room temperature, which elements are liquids at room temperature, where are the metals and non-metals, and so forth. But what I want to stress here is the blocks that we have in the periodic table. We call the first two columns, and each column is a group or a family. So the first two columns, we call them the S block. The 6 columns that are all the way to the right, we call them the P block. And these 10 columns of 4 elements each, we call it D block, the D block. And these 2 series down here, we call them the F block. And that is because that designation corresponds to the type of orbital in which we have the last electron that was added. From the top to the bottom, we have the periods or shells, which would correspond to the n value. So the top row would be n equals 1, n equals 2, and so forth. Here we have a jump. If this is very small, but if you look at this element, is number 57. After 57, instead of moving 1 to the right, it goes down to this series here in the F block. That means that this one element, the last electron that was added to this element was a D electron, but the next one, the next element, the electron goes to an F block. We have 14 elements in this F series, and then from 71 it jumps back to 72. So it adds one F electron in 71, and the next one goes to a D orbital. It's a D electron. We complete that series, the D block, then the P block, then the S block, and then we have the same situation. From 89 jumps down here to 90. We have 14 elements and jumps back to 104. So this is what I just described. We have the lanthanide series down here, the actinide series. These are F elements that belong to the F block. And this row here would be the 4F, and the bottom one, 5F. This table is it's identical to the one I just had on the previous slide, only that I didn't want you to get confused because it looks like this is just one column, 2S. So these are two columns, okay? And things that the textbook highlights here, for instance, is that the NS orbitals fill before the n+1d orbitals take up any electrons. What does that mean? It means that we have 4s here, and I just realized that it seems like this is backwards. It should read n+1s first, so 4 n+1. 4 would be 3 plus 1. So the 4s orbitals are filled before the 3d orbitals are filled. Okay, so there's an anomaly there. But that again is caused by the multi-electron system being different from the one electron system. We don't need to go any deeper in the reasons for that. We just attribute that those changes, those anomalies, to the fact that the electrons repel one another, and the sequence of the orbitals changes. The energy of the orbitals changes compared to the one electron case. What else do we have? We have here that the group number tells us the number of valence electrons. So group number 1 has 1 valence electron. Number 2, 2 valence electrons. What orbital are these electrons in? For group 1 and group 2, those orbitals are in a s orbital. Those electrons are in an s orbital. Which explains why elements within a family, within a group or family, have similar chemical reactivity, because the valence electrons are similar. And the same applies for groups 3 through 8. Group 3, they have 3 valence electrons, 4, 4, and so on. 7 has 7, 8 has 8. 8 is the noble gases, so noble gases have 8 valence electrons. So we can tell easily from the periodic table the number of valence electrons. Here we have a table that has all of the configurations, partial configurations for all of the elements. And we see that assigning configurations and knowing where the electrons are going to gets pretty easy and simple if we understand how the periodic table is arranged. We see that every time we move one value, one number up in atomic number, we're adding 1 proton, but we are also adding 1 electron. So that electron will occupy the orbital that is of lowest energy. So we have 1s, 1, the next one will be 1s, 2, next one 2s1, 2s2. What comes next? P subshell. So we get 2s2, 2p1, and so forth. So we can read the configurations, even if they're not written like they are here, we can read the configurations of the periodic table. We have some anomalies, or some more anomalies, as I said. We see that going from vanadium to chromium, we would expect that to be 4s2, 3d3, going to 4s2, 3d4. Okay, but that's not what we get. We know that because of the experiments. What we get is that instead of having two s electrons, one of those s electrons moves up to the d orbital, and we get, instead of 4 electrons in the d orbital, we get 5. If you read the book, you will see that we don't fully understand why that happens. We have a model and explanation that works okay. May not be compatible with all of the experimental evidence, but it works okay. And we simply say that the reason why one of those electrons is promoted to the d orbital is because when you do so, you have half-filled orbitals. And that's more stable than having incomplete orbitals. So we would have 4s2 and 3d4, in which we would have the s orbital full, but the d orbital wouldn't be neither full nor half full. So we simply say that it's more stable when we have the two orbitals, the s and the d orbitals, half filled. That gives us additional stability. But that's a story we create for ourselves to be able to interpret these results. And we see the same with copper. Nickel is 2s2, 3d8. We would expect copper to be 4s2, 3d9. But one of those electrons jumps to the d orbital because we get a full d orbital. Okay, and we say that's more stable, but we don't need to worry about that. And also, here we mentioned this before, we go from 6s2, 5d1, instead of moving one to the right, and by adding another d electron, we start filling up the f electrons. And that one d electron actually is promoted to an f orbital. So just be aware of these anomalies that we don't need to fully explain. We just need to know that they are there. And the other thing to notice is that I mentioned this before, when we have a family, a group, column, all of these three refer to the same, we see that the configuration of the valence electrons are the same. So for all of the alkaline metals, the configuration is S1. They all have one s electron as the valence electron. Alkaline earth metals, they all have S2. And that causes them to have similar properties, chemical and physical properties. The same applies for groups 13 through 18. You see that numbering changed here from what I had before. There are two competing periodic tables. There are multiple, like almost 2,000 different periodic tables, but two that we use have group numbers that go from 1 to 18, and the other one that you saw before has numbers that go from 1, 2, and it jumps all the way across the periodic table to 3 through 8. And uses the letters in addition to numbers. But at any rate, the group will always have the same number and type of valence electrons. Halogens, their valence electrons are S2, P5. And again, that explains why halogens have similar chemical reactivity. And with this, we finish this second video, and we're gonna get ready to do the stop and practice.